Welcome class to today's lesson on friction. Now friction is a concept that we've been familiar with from way long ago, back in the olden days when these little critters, distant ancestors of ours, realized that through friction we could make fire, which made their life a hell of a lot easier. But what is friction? Well, friction is the rubbing together of two surfaces, and if we look at this on a microscopic level, as these surfaces run over each other, the indents on the surface actually get caught and rub on each other, and this leads to energy loss and the production of heat. And this is what we know as friction. So we see this in our everyday life. We see friction in terms of tobogganing, where there's low friction and we can pick up a great amount of speed. We also see it in terms of tires along a road. As the wheel is turning, we see that the treads on the tires grip the road. We definitely see it in the wintertime, certainly in Canada anyway. When we don't have grip on the tires, enough grip, we will slide off the road, and that can lead to problems. So friction is a physics force that opposes motion, and it usually opposes motion, and it definitely affects motion. And there's two different types. There is static friction and kinetic friction. Static friction is friction that prevents an object from moving. So the object, before the object is moving, it's friction that is between those materials that are rubbing together. And it has a threshold value, which we call Fs max. Now, this is a value that if you don't go above that value, the object does not move. If the force applied is greater than that Fs max, then you will start to move that stationary object. Second type of friction is called kinetic friction, and that is friction that slows down a moving object. So there's two different types that we need to identify. So what's the relationship between static and kinetic friction? Well, if I take this little moving box superhero who's got a wonderful little cape blowing in the wind, and I start applying a force to the box, there is a time period when there's static friction and the applied force is not enough to move it. But what actually happens is as you apply more force, the static force keeps increasing up to a point which we have already talked about, which is Fs max. After this point here, Fs max, the applied force, if it's greater than that, will be enough to move the object. So basically, an object moves when Fs max is exceeded by the applied force. Second thing that you should notice is that the kinetic force actually it drops down, so it is less than the force of static friction. Now that's something that we know anecdotally when we try to slide an object along the ground. The hardest part is to get the object moving. Once it's moving, it seems a little bit easier to keep it moving. The third thing is that the kinetic force is constant. So you can see it's a horizontal line and it's a constant value. Okay, so we need to talk about the things which will impact friction force. Well, there's two different things that mainly impact force of friction. One is the weight of the object. So we know this if you have, a box and you slide it along the ground and then you put a lot of heavy materials into the box, heavy objects, then the box becomes harder to slide. So the weight of the object is a very important factor in terms of overcoming that force of friction. And the second factor that's really important is the actual materials themselves. Now the materials, that stickiness, if you like, or that value for the materials, they're standard values, and we denote these with the Greek symbol mu, which is a symbol which means and stands for what is referred to as the coefficient of friction. And these are sets of values that the materials have. And so you'll see just some common sets of values. Before I talk about those, I should probably say that they are generally, the coefficient of friction is between 0 and 1. So for example, glass on glass, glass sliding, the coefficient of friction is 0.94. And once we get that moving, it drops down to 0.4. We can see the Teflon, of course, non-stick Teflon. There's a reason why we call it non-stick Teflon, and the force of friction is very low. The lowest one that's on this chart actually is something called synovial fluid on your joints, and this is a fluid that you'll find between your bones around your knee area, and it is a fluid which makes the knee bend a little bit easier and the bones don't rub against each other, so it prevents us from a heck of a lot of pain. So so we know that the two factors which are important to friction values we talked about earlier on, and if we take both of those values, we can create an equation which is very, very important, and it is the force of friction is equal to mu Fn. Another way that you'll sometimes see this written is mu, the coefficient of friction, is equal to the force of friction over Fn, or the weight, as long as we're talking about a horizontal surface. So if we look at some problems here, let's look at this problem. It takes 40 newtons to pull a 6 kilogram object along a desk at a constant speed. What is the coefficient of friction? Well, good practice, as we normally talk about, is to create an FBD and then have a look at the Fnet values. So if we create an FBD, we'll see that there's a very, very key point here. And that key point is this, that the object is moving at a constant speed. Now what that means, of course, is that the forces are balanced. Now we can talk about forces in the y direction as well, the Fn, and we can talk about Fg, but we're really talking about the object moving in the x, so we're going to ignore these for now. So what this means is that Fa is actually equal to Fk, the kinetic friction, force of friction, because it's moving at a constant speed. And we'll come back to well, why that's important. Another way of writing this is to look at the Fnet statement. And if we write out the Fnet statement, we'd see that these forces are balanced and they're 0 Newton. And so we bring that up here, and we'll say that these are actually equal, but opposite directions. So Fa is equal to negative Ffk. So if we know that, and we know that Fa, the applied force, is 40 newtons, and we know that Ffk is mu Fn, we can just simply solve for mu. Now we also know that Fn is equal to mg, which is something that I've put in here, and then we just put in the values. When you do that, you'll see that you have newtons above the line, and you have kilogram meters per second squared below the line. Those units are actually equal, so those units will cancel. And we're left with a value for the coefficient of friction, which doesn't actually have a unit, and so it's 0.68. When we're answering the question like this, we should really write out the answer at the end. Coefficient of friction between these materials is 0.68. Okay, so I'm just going to look at one more example, maybe a little bit more of a difficult example. 10 kilogram box is thrown across a level floor. So that's very, very important, because after that point, we're talking about after it leaves the hand, it's slid across the floor. It slides a distance of 6 meters, stopping in 2.2 seconds. Determine coefficient of friction between the box and floor. Okay, first thing we do is we draw an FBD. And the FBD for this, we're really concerned with the x direction. And the only force acting on that is, if you said this was force of friction, you would be correct. So when we write our Fnet statements, we are going to get, that's in the x direction, of course. Maybe have 1 second and think about what that would look like. Okay, if you said that the Fnet statement was Fnet is equal to FF, then you'd be correct. and we'll come back to why that's important. So just knowing that the F net value is FF. Okay, so how are we going to solve this? Well, always a good idea to write out our givens. So we were given the fact that the box is 10 kilograms. We also know that the distance it slid was 6 meters. This is in the X, of course, which we can write in. And we also know that the delta T for the slide was 2.2 seconds. We also are given something which is not explicitly stated, but the box actually stopped eventually. So we should know that that V2 value is 0 meters per second for that velocity, final velocity. So what is required is coefficient of friction. Now, very often, I just want to highlight, very often with these type of problems, there very often is a crossover between kinematics and dynamics. And we've got to remember these two equations. FF is equal to mu Fn, and also F net is equal to ma. So for this one is a good example of where you need to find A, you have M, and that will allow you to get F net, and realizing that F net is connected to FF will allow you to solve for mu or Fn. Okay, so let's try and get that. First thing we're going to do is look at FA, or find FA. We're going to look at the old reliable, the kinematics equations. And we're going to realize that we have delta D, delta T, and V2. So the one to use is this one. And then we'll do a little bit of algebraic diggery-pokery, and we will solve for A. It is a good idea to rewrite this perhaps by saying that delta D is equal to negative AT squared over 2. So that's just a rewriting of what's above. Why can we ignore this one here? Well, because V2 is equal to 0, so we can drop that, and that makes that whole statement, that whole part 0. And then it's just a working down through, putting in the values, and you'll notice that negative A is 2.48. Now, is the sign significant? Of course it is, because that negative A is 2.48, so that means that A is actually negative 2.48 meters per second squared. That should make sense because we've already identified that delta dx that it moves is 6 meters, and that was a positive. So essentially what we've said is everything to the right in the photo is positive. And if we come back to it, the force of friction, so therefore A was acting to the left, which would make it a negative value. So we should be able to see that this negative value should make sense for A. Okay, so we have a value for A. What are we going to do with that? We can use that value for A to find mu. So we know that F net in this case is equal to FF because it was the only force that was acting on the box. And we can just simply sub in the values for F net, which is equal to MA, FF, which is mu Fn. And then we get to this scenario where MA is equal to mu mg. Remember, we're trying to solve for mu. Well, hopefully with your mathematics background, you can see if there's a variable on either side of the equation, we can simply cancel it. And so we get a new value, or a new equation, which says that A is equal to mu g. And therefore mu is equal to A over g. And of course we can solve for that, negative 2.48 over g, which is 9.81. And we get a value for mu. And that value for mu, you guys can solve it off your own back. But it is considerably less than 1. And that is the coefficient of friction. Okay, so we're going to continue this the next day. We're going to delve a little bit deeper into force of friction in our next lesson.